Well, hello, this is Freethought Forum, a program by the Atheist Society of Knoxville and the Rationalists of East Tennessee. I'm Faithless Forrest.
I'm David.
And I'm Charles, veteran reporter of Central Illinois.
All right, and we welcome everyone here to Studio B for an abbreviated program of Freethought Forum TV. We were partially preempted by a government meeting, but we normally start at 6:30. And we are sponsored by the Atheist Society of Knoxville and the Rationalists of East Tennessee. These organizations are Freethought organizations right here in East Tennessee, where you find that if you don't believe in God, you're not alone. Today we're going to talk about a question that was sort of formulated in the, I guess, 1960s by a physicist whose name is Drake. It's called?
The Drake equation by Frank Drake, Francis.
All righty. And this is a sort of a journey in speculation. So what did Frank try to calculate with his equation?
So, I mean, I think he really took almost a really hard approach in what he was trying to tackle, and that's finding out if there is other life that can communicate with us. So you're looking for intelligence, and you're looking for similar technology, and that's a lot. I mean,
all right, and I guess it goes without saying, but we'll say it anyway just to be clear. We're talking about extraterrestrial life or
right.
Extrasolar life.
Right.
And so, people have maybe speculated things about this for, since antiquity. I know that some of the ancient Greeks had considered that the stars in the sky are other suns, and around those suns might be planets, and that on those planets might be living creatures. And I'm pretty sure that, oh goodness, his name is Bruno. He got himself burnt at the stake. I think that
approximately year 1500.
Yeah, I think he was the one who was saying, he was a firm Copernican. He was in the camp that agreed with Copernicus that the Earth must go around the sun, and the clear implication of that is that the universe doesn't spin around us, that the universe is probably, so to speak, at rest. Those other point sources are stars, and you can't help but think that therefore there's nothing special about our star being the only place where there's life. But Drake's approach was a little different. Tell us and the viewers, how is Drake's approach a little different?
So I really like how he did this. He's taking a statistical approach to this. I mean, he's using math to figure out whether or not the biological event sort of happens. And if I was a mathematician, maybe I might be able to do something like this, but I mean, you're taking percentages and possibilities. You end up multiplying all these things together based off these variables, and you're going to get a number that tells you how many civilizations, and this is just for one galaxy. This equation isn't even meant for multiple galaxies. This is just one. And it's going to give you like a number of how many civilizations you have in that galaxy that can communicate.
All right, and so what are the terms of this equation?
Okay, let's see. So what you're looking for, your number is the number of broadcasting civilizations. So to get that number, you're going to have to multiply the average rate of formation of suitable stars, and this is just in the Milky Way. And now suitable, you're going to look for, and this is this is something that's changed a lot since when this equation was formulated in 1961. So the idea that you have to be within a star's habitable zone is no longer really where exobiologists are looking for life. I mean, in our own solar system, we fall into the habitable zone. We know there's life on Earth. But
maybe we should define habitable zone. Charles,
Right.
Charles,
Yeah.
you're listening in on this. Do you know how Drake defined the habitable zone?
The habitable zone was an area where there would be a planet the size approximately that of Earth, plus or minus a certain degree, where water could exist in a liquid form for a significant amount of time of its orbit around the planet.
And
It would allow the formation of complex chemical compounds with carbon. So
All right.
Carbon is the atom, the chemical element that forms the compounds that make up life as we know it.
so the key here is that there would be liquid water.
right.
Yeah.
And there's another phrase added to that often, on the surface. Liquid water on the
On the
surface.
surface.
Yeah. So in our solar system, do we have an idea where that is?
Well, that's approximately, let's see, 0.75 astronomical units, an astronomical unit being the distance from the Earth, the average difference from the center of the Earth to the center of the Sun,
Okay.
to approximately 1.9 astronomical units, that being the distance between, say, just outside of Mars' orbit around the Sun.
So you mentioned that it's just outside of Mars's orbit. So Mars is in the habitable zone because liquid water may
If it
form.
had a large enough atmosphere
Yeah.
and a magnetosphere to protect this planet from the sun's solar radiation and the background cosmic radiation, things of that nature, it would have liquid water.
And in fact, David, when Drake, what's the date on Drake's equation?
1961.
1961. So it would have been in, I think, 1964, 65, or 66 when the Mariner probes went to Mars and produced images and made some accurate measurements of the atmospheric pressure of Mars, to where we realized, oh, well, liquid water is not going to be real common on the surface of Mars.
Right.
But at the time he was starting this, it was not clear what the condition of Mars was. So Mars falls in the habitable zone, but just barely. It's marginal because the atmospheric pressure is low. What about the inner radius, Charles?
The inner radius would include Venus, but Venus's atmospheric conditions are significantly different, being primarily made of carbon dioxide and sulfur. Its surface temperature is hot enough to melt lead. Therefore, life as we know it would not exist there.
And so the reason, so it's in the habitable zone, or at least real close, but yet it's not even closely habitable. And the reason is once again, its atmosphere is different than.
It has a gigantic greenhouse effect, as it's called.
Yeah, yeah. But given the sample size of our solar system, and disregarding the problems with the two atmospheres, there are approximately 3 planets in the habitable zone on our own solar system. So what were the
Goldilocks zone.
Goldilocks zone? What other terms were in Drake's original equation?
So you're also looking for a fraction of stars that form planets. And I really, this one stands out to me as kind of a really interesting variable because, like I said, when he made the equation, he knew of no other planets besides the one in our own solar system. And to this day, we know of over 3,500 planets, exoplanets outside of our own solar system. So this number, it's really interesting that he added it to me.
So I, of course, heard of the Drake equation well before we knew some of these additional terms so much better. And it was very common to take 0.1, meaning 10%, as the probability that stars had planets. And that may have been had planets in the habitable zone. They took it as a small number, and they would say, we're making this up. We don't want to assume it's 1 because that seems sort of cheating the system. They didn't want to assume it's 0 because that would be claiming that somehow our solar system was very unique. So they would use about 0.1. And they did that for a lot of the terms where it was very speculative. They just said, let's call it 0.1 and move on. But it would have been, goodness, I think it was in the very late 80s that telescopic techniques began to detect the subtle Doppler shift in stars, spectral emissions that told us, that confirmed the existence of some large exoplanets around stars. And then
Jupiter scale and Saturn scale and so forth,
yeah. And then the Kepler telescope system really amped that up. And the one thing I don't know, and if your research, your reading told you, of the stars that they looked at with Kepler, they've looked at so many, they can begin to apply statistics to that. So they could say, I assume that they could make an assertion about what percentage of stars are likely to have planets now, based upon Kepler's work.
Right. I'm sure if we looked it up, it'd be much closer to that 1 number rather than 0.01 or 0.1, whatever they had it as before with the 10%.
Yes.
Or 0.1, I assume.
One of the interesting things that has shown up is that our closest neighbors, the Alpha Centauri system, which is made up of 3 stars, Centauri Alpha, Centauri Beta, and Alpha Centauri Proxima. One of the, I think it is Beta B, has shown through the Kepler Space Telescope observations that have a number of planets. And apparently, several of them seem to be close to what would be the habitable zone, because the Centauri system is made up of 3 G sun-like stars, two sun-like stars, one small red dwarf. So just in our local neighborhood, 3 stars that are like our sun, 2 of them are known to have planets in or close to the Goldilocks zone, which is either an incredibly amazing coincidence or indications that planets around sun-like stars are rather more common than previously thought.
That form readily. Well, yeah. I would phrase it slightly differently. We shouldn't say more common than previously thought. Simply, there wasn't a basis to think, and so they would always round down so as to not appear to be making assumptions to favor their outcome.
Right.
So what other terms are in Drake's equation?
I think this one we've kind of been touching on. So the next variable is the average number of habitable planets per star. And I want to point out that it's talking about planets here. So if we were looking at our own solar system and we were going to say how many habitable planets are in our own solar system, I think a lot of people would say 1.
1 to 3 is going to be the kind of argument if the word planet is being used.
Right. So that's not even talking about the places that actually have liquid water, which strikes me as odd. So if we look at Europa or Enceladus, or we want to talk about life that we're not familiar with.
So
and talk about
for our viewers, we must assume that some of our viewers don't know what Europa and Enceladus are.
True. So Europa is going to be a moon around Jupiter that actually has an ice crust with a liquid ocean underneath, and this is being kept warm through geothermal activity because it's next to this giant gas giant that's essentially compressing and stretching the core. So it keeps it hot, keeps the water hot, so it keeps it from freezing. Titan and Enceladus, because it's it's around Saturn, but it's a similar sort of setup. You've got this ice crust, ocean underneath. We actually see jets of water coming out from the South Pole. We know that there's liquid water there. Titan's the interesting one, because that's where you're going to see some sort of variation in life, because it actually has precipitation. It's got lakes and rain and erosion.
But it's not liquid water.
Right. It's liquid methane. So.
All right. And methane is liquid when and how?
Very cold. It's very, very cold. They actually have cryovolcanoes on Titan, which it sounds really interesting, but what you have is liquid water coming out of the surface, and I always like to think of it as the relative temperatures for what you would see on a volcano on Earth. Like, what's coming out is super hot, and everything else is this really cold temperature, and it's sort of comparison to that.
So there would be an eruption of liquid water, which to a hypothetical creature that was living at the ambient temperature would be scalding hot,
right,
horrible, and then just like the liquid rock that is squirting out of the volcano in Hawaii that then makes its way into the ocean, it gets turned into a solid right away.
Right. So,
interesting enough, one of the other moons of Jupiter, Costello, is thought to may well have had a under ice ocean, because it has many of the same characteristics as the Europa, except we haven't seen any of the erupting plumes.
I think Callisto is also assumed to have a very young surface. It doesn't have impact features on it that even the other moons do.
Have been observed, which I wanted to point out.
Right. So but back to the equation, though, those things that we just listed, because they're not technically planets, would we include them in our equation?
And they weren't in the habitable zone the way it was originally defined, because habitable zone had to do with the radiation from the star.
Right.
The heat source here is actually leftover orbital energy that is reworking or massaging these bodies, keeping them warm as they orbit in elliptical orbits around their parent bodies. The situation in Jupiter is very interesting, because there are these 4 large moons, and they actually force one another out of circular orbits in a sustained manner. They will never, so to speak, settle into circular orbits where they stop massaging one another. They're actually in a stable mode of heating one another's crusts, and I assume that actually, in terms of long-term stability, it'll actually get worse, not better, meaning that as they decay, as they dissipate energy, they'll move in closer to Jupiter, and that'll work the system even harder. But I have no idea what that's like compared to the lifetime of our star as a hydrogen burning. Of course, if our sun were to run out of energy and it starts getting cold, then those would be places maybe to go to, because they will sustain heat for a long time.
Yeah, absolutely.
So what other terms have we got there in this?
So the next thing we're looking for is the fraction of habitable planets where life emerges. And I think this is another one of those things where we're going to have to just kind of throw a number at it, because
I'll let you throw. I'm going to make some arguments, though, that I have more confidence in.
Well, so if I want to say the fractional number of habitable planets that life emerges, I can only look at my own solar system, because I can't see other planets well enough to determine whether or not any kind of life has emerged. And I would be stuck with this 1:8 ratio. And if I talk about habitable planets, and I'm talking about planets, then I'm stuck with just 2. I'm not going to say Venus has produced life. I might be microbial life on Mars, and then the apparent life on Earth. So I've got 2 out of 8. That's a really, for me, that's a really arbitrary way and kind of odd way of figuring out a number like that.
Charles, you want to have a stab at it?
one of the things to factor in is that for 90% of life on Earth, we were single-cell species. That's the first 2 billion years or so of life on Earth wasn't multicellular like you and me and dogs and trees and things, but like microbes. So I agree with Devilish Dave there that we have a good 1 in 8, and that's about a 17% chance, or 2 in 8, which is about 30% chance of life forming in those areas, but that doesn't mean they're going to become like us. It just means they might be single-cell species.
Right.
All right, I'm going to speak it to this now, and this isn't original with me. I've read this. I'm ashamed I can't remember who to attribute it to, but we have another way to sample the system too, and that is across time. And in the case of the Earth, there's evidence of life appearing on the surface almost as soon as the Earth might possibly have supported life. When I was young, they would say that there was evidence of life 3.2 billion years ago, then it crept up to 3.5. I've heard 3.9. And so what that seems to imply is that where life might be possible, it establishes itself quickly.
Right.
So that line of reasoning says that we ought to find evidence of life on Mars. If that line of reasoning is correct, we probably should find evidence of life on Mars. If we find evidence of life on Mars, it's a very interesting question of, is it independent of life on Earth? Because Earth and Mars occasionally exchange objects due to meteoric bombardment. The solar wind can push dust from the Earth in the direction of Mars. It is certain that the solar wind has pushed bacteria to Mars. The question is whether or not it's killed them before they got there. The solar wind is capable of pushing small things to pretty high velocities, and bacteria are easily small enough that they've been transported. I have no doubt.
One of the things I like to point out at this point in time is my favorite little species, microscopic in fact, the tardigrade, also known as the water bear, has survived in outer space, in Earth orbit.
And the question is, are they small enough that sunlight can push them to Mars?
Large-scale volcanic eruptions have been known to toss things very, very high.
Yeah.
And
but tardigrades will still need to, they're multicellular, they'd still need to eat something, so they wouldn't be good colonizers. To colonize, you want an autotroph.
Yeah, but they'd be bringing organic compounds, viruses and so forth, and bacteria with them.
All right, I guess in the digestive tract of your tardigrade, you might have some bacteria
that made it all the way to Mars.
That made it to Mars. And if they can then find some way to live in that harsh environment. So there's a kind of question that happens. You know, we get calls to the show sometimes, or when I'm talking with theists who'll say, well, you don't know how life started, so therefore they think that their book with the magic snakes is perfectly tenable. And well, okay, we don't know how life started in the sense that we haven't, let's say, duplicated the creation of life or the starting of life in the lab that we know of. Well, now, and then I'm going to qualify that. It turns into an argument about, well, actually, we don't have to assume that we've created a whole bacteria to have made life. It turns into...
There wasn't a whole bacteria 3.9 billion years ago.
Well, actually, The things that are like 3.5 billion years, those are bacterial-like. They have a cellular membrane around them. I actually don't know what the evidence is for these 3.9 billion year old things.
I think that one's what they've found in zircon crystals. It's these little, essentially indestructible crystals that I would have to look it back up and figure out exactly how they came about that number with that, but that's the basis of which.
And would they be cellular structures, or would they be chemicals that would be thought to be of biological origin?
Right.
Yeah. So there are deposits of things that look kind of like limestone that are thought to be the results of biological metabolic processes that they have no cellular structure in them, but yet they're preserved because limestone is a rock. So I think there are limestone rocks from the very early Earth that are cited as an example of possible early life, older than examples of things that look to have cellular membranes. And it seemed to me there was something else I was going to comment on here, and I've come off target on this.
Well, so the next one kind of goes into where we would go from having some sort of life, and that's the fraction of habitable planets where life becomes intelligent. So you get this evolution of intelligent life. And then you have to...
There's a step in between that Drake didn't consider, but I think it makes sense to pause and talk about. Charles alluded to it earlier. Most of the Earth's history, life was single cellular.
Mm-hmm.
Now, an interesting thing happens at about 1.2, 1.5 billion years ago, and that is life developed cells that had a nuclear membrane. The cells older than that they're called prokaryotes. There is an outer membrane, but the genetic material is all mixed up inside. The nuclear membrane cells also seem to be where sexual reproduction happens and develops. And sexual reproduction allows for the creation or development, I think, of multicellular life, at least makes that far more likely. Multicellular life, the oldest evidence, I think there's something maybe on the order of 700 million years. Do you know of any numbers?
I can't say that I do off the top of my head.
So often we get, when we're talking with creationists, they'll want to talk about the Cambrian explosion as if that's the Genesis event.
Right.
Well, the Cambrian explosion is not the beginning of life. It is when multicellular life begins to leave fossils. Charles, I'm talking over you. You want to jump in?
I've got a major point to point out to creationists. The Cambrian explosion, they're comparing the time of the Cambrian life expansion event to the previous 2 billion years.
Right.
That's like saying that just because I walked a mile, you can't run the previous marathon is worthless, because if you were to compare, the Cambrian explosion was something like 80 to 100 million years long, because it wasn't just a big bang in an instant.
Well, Cambrian is one
period of time compared to us.
Cambrian is one of those periods in the geological time scale that has this interesting repetition, and that is that every about 50 million years there are extinction events. And the Cambrian is a period about 50 million years long. It begins about 550 million years ago. But there are fossils of life older than that. And in particular, there are fossils of things that look like jellyfish. Mm-hmm. Jellyfish don't leave fossils very often. So even post-Cambrian or Cambrian and post-Cambrian, they don't leave fossils often because they don't have hard body parts.
They don't have any bones, teeth, or anything like that.
So what happened about 550 million years ago is that the many different forms of life that were already present began to develop hard body parts. And that seems to be, I'm trying to say the word simultaneously, but around the same time frame. Now, what may have been going on here is that the chemistry of the Earth's oceans were changing, that made them that made it more energetically allowable for life to create hard parts. The oceans may have become less acidic, and that has, I think, something to do with the fact that there used to be a lot more iron in solution in the oceans, and as the Earth's as the algae and stuff were liberating oxygen, it was binding with the iron and precipitating out, and eventually the chemistry of the ocean changed, and that may be related to why it then became possible to build hard parts.
I think that's also around the time you started to see the evolution of jaws.
And it become, well, if in fact in one of Richard Dawkins' books, the speculation is that bones are actually a secondary development from teeth. The teeth are the first occurrence of hard parts. They're the first armament, and that bones become shields against that. I'm looking at the clock here, and we got less than 4 minutes left now. And I thought we should move quickly. And since this is called Freethought Forum, I was going to drag this to a theological discussion in the last minute or two.
Yeah. So our next thing is going to be the fraction of planets with intelligent life capable of interstellar communication. So I think this kind of ties into it has to be kind of like us, and it has to think kind of like we do, and it wants to communicate using a means that we can detect. And they're looking for radio waves, which
because they travel interstellar, and we know how to make them,
right.
At least. So there's an argument about this that says the following. Multicellular life has been around for about 500 million years. Mm-hmm. Multicellular life got big, it got big teeth, it got fast-moving, certainly before the end of the Permian. That's 250 million years ago. And yet intelligent life did not emerge. It appears, if we use the only multi-sample we've got, which is years, that intelligent life happens infrequently, that there isn't a strong evolutionary pressure to produce intelligent life. And by intelligent life, I'm going to modify that further and say life that creates symbolic communication. Symbolic communication is where we've created language and we store information in symbols in written form. But we've got a rather short time, and I want to now challenge both of you with the following. So there are a lot of planets, a lot of stars out there, a lot of planets out there. Perhaps we're going to find some radio signals from some of them, and we'll know that the Drake's equation now multiplies out to something at least greater than 1 here on Earth. And this is for the Christians out there as well. Do those people need to know about Jesus? Do those intelligent life forms need to know about Jesus? Do they need to be saved? Charles, quick like, do they need to be saved?
Well, since Jesus is mythical, no.
All right, well, all right. But there's this thing. Jesus came along to fix the sin of Adam. The sin of Adam happened here on Earth. Mm-hmm. So do extraterrestrialists need to know about Jesus to be saved? And
well, mythology is correct, no.
And
not a descendant from Adam.
And so there we go. Yeah, if they're not descendant from Adam, they don't need to know about Jesus to be saved. Or if they say, of course, everyone needs to know about Jesus because that's the only way to go to heaven, because the Bible says that, you can only be saved through Jesus, then what do they need to be saved from?
Right, they definitely don't have to worry about the end of the world, right? I mean,
no, we have to worry about the end of our world.
Well, we're at less than a minute to go. This has been Freethought Forum, a program by the Atheist Society of Knoxville and the Rationalists of East Tennessee. You can find us from 6:30 to 7:30 most Wednesdays when we're not being preempted by a government meeting. You can find our website, rationalist.org, and knoxvilleatheist.org. Where you can find times and locations of our meetings and get-togethers. Is there anything else that I haven't summarized here? Charles, do you remember how we usually close out?
No, I don't.
All right. Well, we want to say that if you don't believe in God here in East Tennessee with these organizations, you need not feel alone.